Welcome to the video to talk about the LED calculator and its math. We will first start off by introducing the full adder. So let's actually start off by talking about what we want to achieve with the full LED calculator. So overall, we want to be able to add numbers in binary, A1, A0, added to B1, B0. So this is the addition that we want to do. Where A1 and A0 can both be 0 or 1, and the same for B1 and B0. And we said that the representation was that we had, this is our 1s column, this is our 2s column, this is our 4s column, and if we had more, we would have 8s column. So we're going to add numbers in binary as high as 3. So if these are both 1, that represents 3, plus 3. And display the result in terms of LEDs. So the outputs for the LEDs are going to be the sum S0, that's going to be one of the LEDs, this sum S1, and a sum S2. So because we're only adding up to 3 plus 3, the maximum we can have in the sum is 6. And as a result, we only need to represent up to the 4s because we can represent numbers from 0 to 7. So we want to do this overall addition. Now, the way that we do this addition, we have to break it up into steps. So let me erase this for just a second. So we first, when we do ordinary math, we're first going to add the 1s column. So we add A0 plus B0, and we get the sum. Now, we may have a carry. So like we looked at the case, like if A0 is 1, and B0 is 1, then when you add 1 and 1, the sum is going to be 0, and you're going to have a carry in the 2s column. So we may have a carry in to add with the 2s column. We saw that we can do this first sum, S0, and calculate the C in with the half adder circuit. So the circuit looked like we have A0 and B0 going into our half adder, and the output of the half adder was the sum S0 and the carry C in. So we know how to do this first addition by computing the sum and the carry. The next thing that we need to be able to do, we need to be able to add 3 separate binary numbers, or 3 separate bits in this case. So we're working in the 2s column. So we need a new type of operator because the half adder can only add 2 bits. We need something to be able to add 3 bits. So we need to have a new device that has A1, B1, and it also has C in. So we want these 3 things to add. And what do we want to produce? Well, we want to produce the sum S1. And we may want to calculate a carry here, and then bring this down for this carry down to our sum S2. So with these 3 bits, C in, A1, and B1, we need to calculate S1, this is the sum, and, so this is the sum, and we also have to calculate the carry. And so this carry we're going to store as S2. So this new block takes 3 inputs and gives us the sum and the carry. This is known as a full adder. So the full adder circuit is going to be able to add these 3 bits and give us the sum and the carry. And so this will allow us to generate our overall LED calculator. Because what we're going to do is we're going to add A0 and B0 and calculate S0 and C in. And the C in, we're going to plug in to our full adder and add with the full adder C in plus A1 plus B1 to get the sum for the 2s column and to get the carry, which goes into the 4s column. So now that we know what we want to do to make this 2-bit by 2-bit adder, we need to decide what is this full adder going to do. How can we add 3 bits together? So let's think about how we can decompose this problem. Decomposition into problems that are simpler is a good strategy for figuring out how to do something complicated. So what we want to be able to do, so I'm going to put this at the side. What we want to be able to do is we want to be able to add Cn plus A1 plus B1. These are all currently in the 2's column, and we're going to have a 4's column that we're going to work with. If I'm going to add these three numbers together, these 3 bits, these can either be 0 or 1. So the most that I can get from adding these 3 is that I can get a total of 3. So I could have a 1 in the 2's column, and I can have a 1 in the 4's column. So 1 and 1, this is like a 2 plus a 1. So the most that I can get from adding these 3 things together is a 3. I'm not going to have another carry which goes off the page. That's why I put this all the way to the left edge. So the 4's is the most that we're going to do. We saw from the previous case, we're not going to have another carry to the 8's column. So we need to add these 3 things together. Well, computers like to do 2 things at a time rather than 3 things at a time. So let's think like a computer, and let's think about what if I add A1 and B1 first, and then work with that result to add to Cn. So I know how to add A1 and B1. So if I have A1 and I want to add B1, I'm going to put it into a half adder. I'm going to add A1 and B1, and I'm going to get the sum, S. I'm going to call this an intermediate sum. So this is S intermediate. Because this is not my final result. So I add these 2 together and I get a sum, and then I know how to get the carry. So I have my carry, and I'm going to just shorten it to be intermediate. So what I can do is I can add A1 and B1 together and get an intermediate carry and an intermediate sum. And this we know how to do because we know how to do a half adder. To be able to add this now to Cn, what does that look like? So we have an intermediate carry and an intermediate sum, and we want to add Cn. So the way that we do this addition, we're going to do these 2 as a half adder. So let's not think about the C intermediate for just a second. We would add S intermediate with our Cn, and we would get our sum, and this now is S1 because this is going to be the final sum from these 3 things added together. I may get a carry, so I have another carry that I have to keep track of. And then I have to add these 2 carries. So I would get a sum, which would be S2, and I need to pause and think, will I get another carry? And the answer is no, because I already said if I have only 0's and 1's and I'm adding 3 things together, the most I can get is 1, 1. So I can only have these 2. These 2 I'm going to add and get a sum. I'm not going to get yet another carry. So now we want to be able to think about what are the logic operations in order to realize this addition of these 3 bits to be able to build this full adder. Well, what we said is we're going to do a half adder. So this was a half adder. That's going to add A1 and B1 and give us a sum intermediate and a C int intermediate. We're going to do a half adder between S intermediate and Cn and get a sum and a carry. So that's another half adder. So actually, let me make sure this thing makes a lot of sense to people. What I'm going to do, so I'm doing these 2, and I get the sum and I get the carry. So there's a half adder in here that's adding these 2 and giving me the sum and the carry. And then I'm doing these 2, which is just the sum part of the half adder. So overall, I need this half adder, I need this other half adder, and I need just the sum part of the half adder to make my full adder circuit. So the way it's going to look, I'm going to take what I said here. This is the first thing I do. I do a half adder between A1 and B1. So my full adder, I'm going to take A1 and I'm going to take B1 and I'm going to do a half adder. And the output of the half adder is this C intermediate and this sum intermediate. So I get S intermediate and I get C intermediate. That was this first step. So I add A1 and B1, I get an intermediate sum and an intermediate carry. I then need to take this intermediate sum and the C in that I haven't worked with yet, and I need to do a half adder on that to get S1 and this other carry. So let me give myself a little bit more room. So I have C in, and I'm saying I want to do the half adder between S intermediate and C in. And the output is going to be S1 and the C. So I do a half adder here between C in. So I do a half adder between C in and the intermediate sum. And the output sum is my S1. The output carry I have here, this is C. I haven't labeled it. Yeah, I'm just going to call this C. Now I need to add C and C intermediate, but only compute the sum part of these two. And we know that if we're doing a sum of these two, we can use XOR. So I need to take C intermediate, or sorry, C in and C and do an XOR. And this output will be S2. So let's summarize what we want to do and make sure this all carries together. We have a 2-bit number. So this represents numbers between 0 and 3. We have another 2-bit number. We're adding these two 2-bit numbers together. This is the LED calculator. So this whole part, this is the LED calculator. We want to be able to add A0 and B0 using a half adder to get S0, which we're going to display as light, and get an intermediate and get this C in. We're going to take C in plus A1 plus B1. We want to create the sum and display this as S1. We're going to display the carry as S2. That's how many 4s that we have. The tricky part is we now need to develop a circuit that's going to do this full adder. The full adder is going to take C in, which was the output of this first half adder. It's going to take A1 and B1 and compute the sum S1 and the carry C. So I need a block that's going to take these 3 bits and give me the sum and the carry. We said to be able to add these 3 bits together, we're going to add these two first, and then we'll add this C in last. So adding these two first, we add A1 and B1, and we get an intermediate sum and an intermediate carry with a half adder. So we take A1 and B1, we get an intermediate carry. Oh, that's why this is wrong. Okay. Okay. This part, what's the wrong one? I have too many things that look similar. So this was C in, this is C intermediate. The very last step, we were adding C with C intermediate, not with C in. Okay, so we were adding C intermediate and C. Okay, so let me start the full adder again. So we want to add Cn, A1, and B1. A1 and B1 gives us this S intermediate. So we add these two, we get S intermediate and C intermediate. That's this half adder here. Then we want to put in and add, so after we've added A1 and B1, we have C intermediate and S intermediate. And we want to add Cn. Cn was this output from the first half adder. But we want to add C intermediate, S intermediate, that 2-bit number, we want to add a 1-bit number to it. So we're going to add these two, S intermediate with Cn. We're going to compute a sum, S1. We're going to compute a carry, C. And now we need to add C with C intermediate. There's going to be a sum, which is S2, and this sum is executed with an XOR. There's no extra carry because we said when we add three things together, the most we can have is S2 being 1 and S1 being 1, representing the number 3. So there's not going to be any 4. So we don't need a half adder here. We only need the sum parts because we know there's no carry. So our full adder circuit, we're going to take Cn and we're going to send it into this half adder. We're going to add A1 and B1. Actually, we're adding that first. The intermediate results, we're taking the sum, doing a half adder with Cn and getting a sum and a carry. And then this carry with this carry, we're going to do an XOR and we'll see what that sum is. And so that's how we're going to build our LED calculator. This block diagram, this whole thing, this is our full adder. So in the circuits, we're going to be able to build the full LED calculator with a half adder and a full adder, and the full adder consists of 2 half adders with an XOR. So this concludes the video on how to build the LED calculator, or I should say how to do the math behind building the LED calculator.